Hi. So now we are going to discuss one algorithm, gradient descent algorithm. It is called to find an optimal solution to the linear regression problem, right? So remember in the last problem we talked that we have some input data x and we have some values y, and we want to find a hypothesis which maps given input x to y. So x can belong to x could be n and rn dimensional in n dimensions, and y is a some real value, right? So what we did is we try to fit a line which best fits the training data, and we represented this hypothesis as theta transpose x, right? So the goal of the algorithm is to find the optimal value of theta. So gradient descent algorithm will help us to find optimal theta by minimizing the loss, right, or by minimizing the error, right? So remember we have denoted the error function as j theta, which is equal to half of the total squared error over all examples, right? So over all examples, what we do is we find the error by taking the difference of the actual value and the prediction, right? So this is the actual value and this is the predicted value, right? So the difference is s theta of x of I minus y of I, and this is square, right? So what gradient descent does is it minimizes the error, and this is the error function that we are going to minimize, right? So before starting with the gradient descent, let me talk little bit about convex optimization, right? How to optimize a convex function, right? So what is a convex function, right? So let us first see what is a convex function, right? So if you have a function like this, suppose this is a function and this is one more function, right? Suppose this is one more function, and I would say that this is a convex function, right? And this is not a convex function, right? So this is not convex. What is the criteria? So the criteria is if you draw a line between any 2 points, right, the value of the function always lies below the line, right? So this line is always above this function, right? So this function always lies below the line, so it is a convex function, right? But if you suppose you draw a line between these 2 points, right, you will see that this function, right, so this part lies above the line, so this function is not convex, right? So this is how you can visualize a function, right? And you can check if you are able to draw a line, right? Then we will say that, and if the function lies below the line or on the line, then it is a convex function, right? So how do we do it mathematically? We will talk about that later on, right? So if I'm not diving into the mathematics, but it uses a concept which is called Hessian, which we will discuss later on, right? So now how do we optimize a convex function, right? So remember the function j theta, right? This is the function I goes from 1 to m y h theta of xi minus yi to the square. Total squared error over all examples is a convex function because this kind of a curve is a parabolic curve, right? So you can say this would form a parabola kind of stuff, right? And let us see how we can optimize this function, right? So let us see how we can optimize this function. So this is a function of theta, right? So y is a function of now theta, right? Because all other values are constants, all other values are constant except theta. Theta is changing, right? So if theta changes, line will change, right? Line will also change, right? So what we will do, we will start from a random theta. Let's say this is the theta init, and we will go in a direction which minimizes this function, right? So we will go in a direction which minimizes this function, right? So we have to move towards this point, right? So what we will do, we will move towards this point, right? Using a update rule, right? We will, at this point, what will happen? The gradient will become 0, right? So let's say if this function is called f of theta and this is theta, right? So at this point I can say that del of f of theta with respect to del theta, which is the gradient or the slope, right? This becomes 0, right? So what we are going to do, we will take small steps, right? So suppose you are standing at this hill and you want to go into the valley, right? So you want to go towards this. So what steps you will follow is, what you will do is, you will make updates using this rule: theta equals to theta minus eta times del of del theta of f of theta, right? So this value is nothing but the gradient, right? So this value is nothing but the gradient or the slope, right? So if you compute gradient at this point, you will see this is a negative, right? So the slope is negative, right? So this slope is negative, and if this is negative, this is a constant which is called a learning rate, right? Basically this defines the step size, how much you will walk, right? So if the learning rate is too high, you might take a bigger step. You might take a step like this, then like this, then like this. So if the learning rate is too high, you will overshoot the minima and you will end up on the other side, right? So step size should be small, right? If you are going down in a hill, the step size should be small. So generally the value is like 0.01 or 0.001, right? So this is a hyperparameter you have to try, right? So you have to try what is the best learning rate for the given problem, right? So generally it is kept small, so it is a small value, it's small constant, right? So what will happen is, if you are initializing from this and if you use this update, right? So what you will do, you will slowly move towards your minima, right? And when you come at this point, this value will become 0, close to 0, right? So slope will reduce and your theta will change very less. Change in theta would be very less or almost 0, right? And suppose you're doing a random initialization and in the beginning you were at this point. So suppose this was the theta in it, right? And in this case, this slope would be positive, right? So what will happen is, the update will reduce theta, so theta will move in this direction. But if you are at this point, theta in it, and this slope is negative, so due to minus is positive, you will move in this direction, right? So it does not matter at which point you start from. If you have the correct learning rate, you will eventually land up at this minima, either from the left or from the right or any other point, right? So if the function is convex, right? So we say that this function is convex, it will ensure that local minima is equal to the global minima, right? This is the property of a convex function, right? And we are saying that the current loss function in our case is a convex, right? So what is the role of a gradient descent algorithm, right? So gradient descent will take us to a local minima, right? Since it is a convex function, this local minima is also global minima, and hence it will help us to minimize the error. So minimize the error. So that would give us the correct value of theta, right? So now the question arises, what theta it would be, right? So what theta it would be, right? So if it is a n dimensional case, then you will have theta n plus 1, right? If it is a single case, right, if x belongs to Rn, or if x belongs to R, for example in our case, then you will have theta 1 plus 1, which is 2, right? So there will be two thetas, theta naught and theta 1, right? Because we have already seen in the current example, if you are drawing a line, then the hypothesis is nothing but theta naught plus theta 1 x. This is x and this is y. X belongs to R and y also belongs to R. In that case, there will be two thetas. So you will have one theta naught here and one theta 1 here, and this parabola will be now a bowl in 3D. This will be a bowl in 3D and it would be j theta, right? So what you will do, you will start from one point. Let's say you randomly choose theta is like this, and then eventually you will end up at the base of the bowl, right, at this point, right? So at this point you will stop. This is the required theta naught and this is the theta 1. These are the optimal values of theta, and this is, let's say, called theta star, right? These are the optimal values where we are stopping at, right? So now let us see how we will make updates using the gradient descent algorithm, right? So let me write the loss function once again. Okay, so loss function j theta, this is equal to half of summation I goes from 1 to m s theta of x of I minus y of I whole square, right? And this is the update we want to make, right? So this is the update we want to make. So we want to compute del j theta with respect to theta, right? So I want to compute this value del of j theta with respect to del theta, okay? Now I do not know which theta is it, right? So there are two thetas, one is theta naught, one is theta 1, right? And let me also define what is hx, right? So what is hx? H theta of x is nothing but theta naught plus theta 1 x. So this would become half of into 2 summation I goes from 1 to m h theta of xi minus yi, this square goes off, right, into derivative of h theta x, right? So del of h theta of xi with respect to del theta, right? Now there are two thetas, one is theta naught and one is theta 1, right? So what I will do, I will take derivatives with respect to two thetas, right? So if I take del of j theta with respect to del theta naught, so it will become summation I goes from 1 to m h theta of xi, the prediction, minus the actual value, into derivative of this with respect to theta naught. So derivative of this with respect to theta naught is nothing but constant. So this derivative is 1, right? So 1 is nothing but x naught, right? So you can either write x naught or you can also write 1. And the second thing I need to have is del of j theta with respect to theta 1, right? So we are getting two gradients, one with respect to theta naught, one with respect to theta 1, right? And it would be h theta of xi minus yi, this part, into derivative of h theta x with respect to del theta 1. So derivative of this with respect to theta 1 would be nothing but x, which is nothing but x1. So it would be x1, right? And if I generalize this, what I will get is, if I generalize this, and here we write x naught is 1, right? So del j theta with respect to some theta I, it would be summation I goes from, let me take some another variable, theta k. I goes from 1 to m it would be h theta of xi minus yi into xk. So this is the gradient with respect to the theta, right? This is what we need to do. So what our final update rule will become, we will see. So finally what we are going to do, so in gradient descent, if you want to find an optimal theta, you are going to update all the thetas, right? So you are going to update theta k equals to theta k minus eta times summation of I goes from 1 to m h theta of x of I minus y of I into x of k. Right. This is the update rule that we will use, right? X of I, right? So for the ith example and the kth feature and the kth theta, right? And if you want to take the minus sign out, what you can write is this becomes theta k plus eta times summation I goes from 1 to m yi minus h theta of xi into x of I and k. So this is how you will update the theta k, and theta was a vector, right? So this update you will apply for all thetas, right? Theta 1 se leke theta n, and I have given you the update for a given theta k, and similarly you will apply updates for all the thetas, right? So you will have updates for all the thetas. So this is your gradient descent algorithm. So what is the algorithm? Gradient descent algorithm, right? So first is initialize theta randomly, right? Then while you have not converged, while the algorithm has not converged to a local minima, you will update theta using the above rule, right? So using this rule you will update theta while the algorithm has not converged, right? This is what you want to do, right? Right? So I can write the second step as while. Now you have to decide what is the convergence criteria, right? So criteria of convergence, you have to figure out what it would be, right? It could be that change in theta is very small, right? Or it could be the gradient is very less, right? So criteria of convergence, which we will decide, right? So it again is an engineering question which you have to figure out, right? What you will do for all theta, right? So for all k in the range 0 to n, right? Theta k will go and update theta k plus eta times I goes from 1 to m yi minus h theta of xi into xi of k. This is the update and this is the algorithm, right? So in the next video we will talk about the implementation of this algorithm. Thank you for watching. I will see you in the next tutorial, right?